we go. This unit's covering Zumdahl chapter 10 and 11. We're going to start off with the beginning of chapter 10 and talk about liquids and solids and forces. So we need to quickly revisit the idea of bonding because we're going to keep mixing in some terms. So we consider bonding to be many things. We've studied covalent bonding and the intermolecular or the internuclear interactions of electrons, looking at where electrons lie. We've looked at polarity and nonpolarity in covalent molecules. We've also considered ionic bonding, which we know that we have two charged bodies that are side by side and in a repeating pattern. Imagine in 3 dimensions, just a repeating pattern of sodium and chloride ions, where the interactions between each ion there in an ionic compound are all the same. Whereas in a covalent molecule, you have this neat covalent bond that's between the two nuclei. Those are types of bonds. We also have forces that take place between different molecules, and this is kind of unique to covalently bound compounds, that also attracts them. And these are called intermolecular forces. And I try to use the word intermolecular forces and intramolecular bonding to make that really clear. But the interactions in between these two these two unique bodies are very notable, and they basically predict a lot of the property behavior of common substances, and we take advantage of those behaviors for lots of utilities in industry. So intermolecular forces, which is what we're looking at where my red arrow is here, they act particularly, for the most part, on the condensed states of matter, the liquids and solids, but not so much on gases. They do act on gases. That's what real gases are. We know that. But we also have to consider the fact that we see it mostly in liquids and solids. So intramolecular bonding, that's ionic bonds and covalent bonds. Intermolecular bonding is relationships, or intermolecular forces are relationships between distinct molecules. So there's really no intermolecular forces. Sodium and chloride is this 3-dimensional attracted by the same force, an ionic bond between everybody in the crystal. Whereas in a sample of hydrochloric acid, we have a different force that exists between these two molecules. So the first type of intermolecular force I want to speak of is the dipole-dipole interaction. And there's a great graphic in the Zumdahl practice I put out, but showing how these dipole-dipole interactions work. But essentially what you have is two dipoles that are attracted to one another because they're dipoles. Okay, super cool. They have, and this is what's important to understand about a dipole is a molecule. It's got to have 2 different nuclei at least to be a dipole. Okay. Otherwise, if it was just a sodium ion here, this would be an ion, not a dipole. Okay, so we're talking about dipoles. Dipoles are some substances like we just saw, hydrogen chloride or hydrochloric acid. In this context, we should probably use the word hydrogen chloride because it's not acting like an acid. Anyway, they're attracted to one another because they're charged. These are about 1% as strong as a covalent or ionic bond. They're not that strong, but they do altogether make things behave very uniquely. In this diagram, you see that the molecules are orienting to maximize attraction and minimize repulsions. The next type of intermolecular force is hydrogen bonding. Hydrogen bonding is just a very strong dipole-dipole force, so strong that it bucks the trend. In other words, the trends we would expect of certain molecules. Molecules that have hydrogen bonds form are dipoles that are extremely strong. So what we tend to see with dipoles is hydrogen bound to one of fluorine, oxygen, or nitrogen in a molecule, and that unique relationship allows for a greater degree of attraction than any other dipole force. They are not covalent bonds. They are still that relatively small force. But we have to take note of the fact that they give many different substances very unique properties, like water and ammonia, and bunches and bunches of other organic molecules that contain one of these or one of these, and bonded to something else, where the R is something else. Who knows what it could be? There's dozens and dozens and dozens and dozens of possibilities. So This is a graphic that illustrates that trend I was talking about, things that hydrogen-bound buck. There's water, hydrogen fluoride, and ammonia. And what you should see that as you increase the mass of nonmetal hydrides, you see that typically we see the boiling point increasing up and to the right. But these three molecules, water, hydrogen fluoride, and ammonia, are very different from the rest of the trend in that they exhibit um, condensation at much lower temperatures. Condensed states of matter. That's what I mean when I say condensation. They form liquids at much lower temperatures. So this is why we have a unique category called hydrogen bonding. So the final intermolecular force we'll discuss is dispersion forces, or London dispersion forces, sometimes also called induced dipoles. Uh, what these are is very weak, very weak forces that exist in all phases and all types of matter. Um, they are essentially electron imbalance on an atom that causes a brief and temporary dipole to form that can attract electrons on a nearby atom and form a brief and very unstable relationship. Now, a singular London dispersion force is almost insignificant. But if you have large molecules with lots of atoms and even more electrons, then you tend to see dispersion forces causing changes in behavior. In fact, dispersion forces are the primary attractive force between nonpolar molecules and noble gas atoms. Things that are not typically you wouldn't expect to attract to one another are attracted together by this simple and small force. It is a notable fact that about 25% of the attractive force between two water molecules is not just hydrogen bonding, it's also dispersive forces. So 75% are that strong dipole force of a hydrogen bond, and about 25% LDFs. So we call this a temporary dipole because electrons are constantly in motion, or they're constantly changing where they are. And because of that, whatever dipole might form can just as simply uh, go away. So this is the reason we call it a temporary dipole. As far as strength, it's very weak. Um, and when we talk about freezing point, we can talk about noble gases. The freezing point of noble gases increase down the group because the more massive atoms have more electrons and thus are more polarizable because they can develop more temporary dipoles and coalesce or condense. Oops. Uh, when you're writing an FRQ, it's very important to note that number of electrons in an atom or molecule, we're going to refer to that as polarizability. How easy does this polarize? Substances that are larger with more electrons are more polarizable. Bonding reflects LDFs and nonpolar covalent compounds. The boiling point of nonpolar covalent compounds increases as the size of the molecule increases. And so what we're going to look at now is a table of halogens. And the halogens that you see here are given fluorine all the way through iodine. And what you should see in the table is the increase in melting point as you go down the group and the increase in boiling point. And in class we looked at solid iodine, which is a crystalline blackish purple solid. We also looked at liquid bromine, which is a reddish brown liquid in an ampule, but we could see very simply, we could see that there were vapors inside that ampule. So these changes in behavior, given the fact that all these diatomic molecules are nonpolar, is attributable to that increased size and greater degree of polarizability, and therefore more condensation at lower temperatures as you go down the group. So general strength trends in strength of attraction, and this is worth memorizing, and this is if all things are equal and we're talking about just one of them. LDF is the weakest force, then dipole-dipole, then hydrogen bonding. And then as we go through the bottom three, we haven't really directly discussed these in terms of strength relative to one another, so this is sort of the learning point. Metallic bonding tends to be just a bit strong, a lot stronger. There's a large gap we need to note here, very large gap, and we'll look at it in a graphic soon. Metallic bonding is a strong type of bond. It's actually a type of covalent bond. but it's we have delocalized electrons in a covalent bond. Then we have ionic bonding, and then finally a type you've never seen before called a covalent network solid. And the go-to example for covalent network solid is diamond. A covalent network solid is essentially a tetrahedral matrix where nearby tetrahedrons of carbon, all carbon at all these points, is surrounded by more tetrahedral carbon bonds in three dimensions. And so you see this shape that develops, and what you essentially have is a giant mass of covalently bound carbon atoms. And for that reason, LDFs are a very small, not insignificant, but very small component of what attracts together the atoms in a diamond. And we'll talk about some more of those soon. And it's also because of this fact that you have a network of covalent bonds, a covalent network solid is among the strongest substances on Earth. So determine the type of intermolecular force for each of the following substances. First, we have hydrogen gas. Hydrogen gas, and when you're not sure, you should draw these things, is a nonpolar molecule. And then hydrogen chloride, you would think that would be dipole, so I would expect LDFs. Hydrogen's LDFs because it's only nonpolar. And then we have iron, which is a metal. We have metallic bonding, and also have LDFs. Remember, all matter has LDFs. And then hydrogen sulfide. Hydrogen sulfide is dipole-dipole forces because it's a polar molecule. Similar to water, hydrogen sulfide would look like this. And so polar, and you would also have LDFs. Silicon carbide is another type of covalent network solid. Typically, we see things that are networks of carbon and silicon, even boron and germanium tend to form covalent network solids. And we'll get through all these types, and so you won't be surprised by them on any assessments. Finally, the covalent network solid also has London dispersion forces there, although they're relatively small. And then finally, carbon dioxide. And if you've drawn carbon dioxide as many times as I have, you probably remember the structure just by seeing the words. But it's a nonpolar molecule with polar bonds, but that doesn't make it polar, so all we have is London dispersion forces. So now we're going to rank these substances from lowest boiling point to highest boiling point. Now you might say, well, we haven't discussed boiling point. Well, indirectly we have. The greater degree of attraction substance has between its parts has the largest boiling point. So we're going to go by weakest attraction to strongest attraction. So immediately we should say, hey, what's the weakest attraction? It's just going to be LDF. So what if this is nonpolar and covalent? Well, that's ionic. That's pretty strong. That's germanium. That's on the page before. I wrote that as one of the things that forms covalent network solids. So that's probably off at the end. And then we have ammonia, which is polar, if you recall. Ammonia looks like this. And then we have a pair of electrons on that central atom. And then water we know is polar. Fluorine gas is nonpolar. Let's try that one. Yeah, because sulfur dioxide is polar. So sulfur dioxide looks like this. Oop, pardon. Well, it depends on who you talk to. But this is one of the, definitely polar anyway, one of the possible configurations for sulfur dioxide, but this is our response. Fluorine, LDFs only. Ammonia is a dipole. Hydrogen bond. Ooh, I don't agree. Sulfur dioxide is not hydrogen bonded. So we're going to put sulfur dioxide, then ammonia. This is incorrect. Then water, which is more polar than ammonia. We saw it on the list a few slides back that water was the strongest of the hydrogen bound. And then we have an ionic compound. There's a significant gap here between things that are held together by IMFs and things that are held together by bonds. We have significant differences. Now, it's important to note that if we want to melt sodium chloride, we're going to end up with a bath of sodium ions and chloride ions. Okay, there is no IMF to break there, so we have to break a strong bond. Same is true of germanium. We're just going to have a sea of liquid germanium atoms if it even holds a liquid phase. So, yeah. fluorine, then sulfur dioxide, then ammonia, then water, then sodium chloride, and then germanium, with a big gap between water and sodium chloride. We know this goes at about 100 degrees Celsius. This stuff goes at 800 or 1,000 Celsius, something like that. It's a large number. So, dipole-dipole attraction, attraction of molecules having dipole moments for each other, a negative to positive, about 1% as strong as a covalent bond. Molecules orient themselves to minimize repulsions, maximize attractions. Now, I want to show you a slide about the different types of attractions that can happen when you mix things together, just so you've seen them. This is sodium ions surrounded by water. We would call this a hydration shell, but that's an ion-dipole interaction, okay? An ion being attracted to a dipole. We know hydrogen bonding when you have an OH molecule attracted to another OH molecule, okay? And then we have dipole-dipole forces, two different polar molecules being attracted in solution. This is where we get into the old like dissolves like in a solution. Ion-induced dipole, and this would happen at an interaction between two phases of matter, chlorine and hexane. They're both potentially maybe an aqueous system here and a liquid hexane here. We would have to have some junction between the two substances, and while you have this polar molecule in water, you imagine it's going to cause a little bit of a dipole along the atoms of that border with the hexane. So you actually have a neat little attraction, and that's why when you make an oil-water mixture, you see a nice defined line, because there is a good degree of attraction right there at the junction. Dipole-induced dipole. We have acetone with hexane. Acetone is a polar molecule, not hydrogen bound, but polar. And then finally, just plain old dispersion forces in two nonpolar molecules. We have octane and hexane. Again, like dissolves like. And that's going to bring us to video number 2, where we talk more about liquids. I hope this has been a useful video for you.